Kia ora. In this video we're going to talk about acceleration. Now you've probably got a bit of an idea about what acceleration is. If you drive a car, you know that if you press the accelerator pedal down, it makes you go faster, and indeed that is part of what acceleration is. But in physics, acceleration has a slightly more specific meaning than that. So when we have acceleration, all that it means is that the velocity that your object is traveling at is changing in some way. It doesn't necessarily mean going faster. So for example, let's just think in 2 dimensions for the moment. If we have an acceleration in 2D let's imagine our velocity is currently like this. So maybe we're traveling along in that direction. We often draw the velocity vector coming out of our object just to emphasize which way it's going and kind of how fast by how long it is. And let's say that the velocity over a period of time changes so that now the new velocity would be the same direction but longer. Then what would have happened is there has been some kind of acceleration that has stretched out the velocity vector. So that would be the change of magnitude of vector option, where our object is speeding up. But if instead our vector got shorter, then that's also an acceleration. In this case, our object would be slowing down. The acceleration would be causing the velocity vector to get shorter. But that's not all. That's not the only way that a vector can change. What if over time our acceleration meant that our new velocity was now going in a different direction, but the same length? So this would be, for example, if I'm on a scooter going to work at Massey, and I'm turning a corner but keeping the speed constant at 25 k's an hour, which is what the scooters do, then that is still an acceleration, because even though my speed's not changing, I am changing my direction, I'm changing my velocity vector, so I've undergone some kind of acceleration. So how do we define our acceleration? Well, we can start by talking about the average acceleration over a time interval, in much the same way we talked about average velocities before. And indeed, the formula is pretty much the same, except we're going to have velocities instead of positions. So our average acceleration over a time interval is our delta v, or our change in velocity, divided by our change in time, or the length of the time interval. So it's our final velocity minus our initial velocity, they're vectors, divided by our length of time. And that will give us the average acceleration over that interval. And the way we think of it is, acceleration is kind of like, by how many meters per second is my velocity going to change each second? So it's measured in units of meters per second, which can also be written as meters per second squared. Or this is the same. These two things mean exactly the same thing. They both mean meters per second squared. So the velocities, these are instantaneous velocities. They are not average ones. And they're the instantaneous velocities at the beginning and the end of the interval. And finally, you can see that acceleration is a vector and is given by a vector subtraction. So the direction of the acceleration tells us which way the velocity is changing, and the magnitude tells us by how much. So for example, if I had a velocity like this is my initial velocity, and it changed into a velocity like this, my final velocity, then my acceleration is basically going to be to do with the vector difference of these. So it's going to be this vector here, that's what that subtraction means, but it's going to be divided by a change in time, so it's not exactly that vector. But you can see the acceleration pointing in that way has caused my velocity vector to stretch out. If my acceleration was pointing the opposite direction, if my acceleration was this way, if my velocity got shorter, then you can see that my acceleration would have been in the opposite direction to my velocity, and that would cause the deceleration, or the slowing down, that we talked about before. And for the corner turning case, which only really applies in 2 dimensions or more, let's say my velocity went like this, then in this case the difference would be like this, and so my acceleration is actually going to be in a direction completely other from my velocity. And because the acceleration is now kind of sideways, it's going to steer that velocity vector and change its direction to being more kind of like that. Okay, so the direction tells us in which way the velocity is changing, and the magnitude of it tells us by how much it's stretching every second or whatever. Alright, so just like we had instantaneous velocity, we can talk about instantaneous acceleration as well. And we're only going to really do that in one dimension, just because it's a bit more complicated otherwise. So we can do it the same way as we found instantaneous velocities from position time graph. So the idea is we have, this time we're going to have a velocity time graph. Now when we're dealing with these graphs, or any problem involving a graph, what you really want to do is you want to make sure that you're very comfortable with what kind of graph you're looking at. Because if you're looking at a velocity time graph, it's quite a different thing to a position time graph, and if you get them muddled up, then you're going to have problems. So if we've got some kind of velocity time graph, let's say we've got one like this, and we wanted to find the acceleration at this point in time here, then same kind of deal as what we did previously. We'd sort of go to that point, we'd draw on a tangent line, and we would calculate the rise over run slope of that tangent line. So we go, oh yeah, what's this distance here? And what's this distance here? That will be my delta v along here, and that will be my delta t. And so my acceleration at that point in time would just be delta v over delta t for that tangent line, not for the graph. Remember, when we're doing average acceleration, that uses 2 points on the graph and uses the delta v over delta t for those. We can basically piggyback on all the work we did with velocities in terms of the actual mechanical techniques of calculating these things. So let's look at an example. We're going to look at a one-dimensional example where we have an interval of time with constant acceleration. So here's carrots as usual, starting off at a position kind of arbitrarily of 0. And we've got a velocity at the beginning of when we started measuring. It's like we've started our video camera when velocity was already negative 4 meters per second, and that's been indicated on our picture here by this arrow. That's my velocity, and we're saying that carrots is going to experience a constant acceleration of 1 meter per second squared. So that's in the right direction, and we're indicating it in that sort of light purple color. That's the acceleration. Right. Okay, so what does this do? How does this actually work? Let's just switch over to the computer. So here is our situation. We've got carrots along here. Just ignore the graphs for the moment. Just focus on carrots and the arrows. We'll refer back to these in a minute. And the acceleration is that vector here. The velocity is currently negative 4. Now what this acceleration of 1 meter per second squared that's going to stay constant throughout means is it means every second this velocity vector is going to become 1 more positive. So currently it's at negative 4. So what we should expect to see is that after 1 second, the velocity vector should be at negative 3. It should have had basically 1 added onto it. So if I scroll along here to 1 second, you can see indeed my velocity vector has got shorter. So what's happening here is because these things are in opposite directions, carrots is slowing down. And you can see my velocity started at negative 4, and by 1 second it's down to negative 3, so that's not quite as fast. Still moving left, so you can see the position is going downwards because we're still moving to the left, just not quite as fast as we were before. And if we go for another second, it's going to get shorter again by 1. And so now we're still moving left, but now the velocity is negative 2. And you can see that as we keep on going on, the acceleration of 1 means it's now down to a velocity of negative 1, all the way through to 4 seconds where the actually carrots have stopped moving altogether. You can see the velocity is now 0 if we look across on the velocity time graph. Acceleration has stayed at 1 the whole time, at +1. And my position, because I've stopped moving, you can see the position is kind of flattened out. If I took the gradient here, I'd get 0, which corresponds to this point on the graph. Keep on going. The velocity vector is turning around, and after another second, let's go 2 seconds, you can see the velocity vector is now stretched out to being positive 2 because it's still getting just +1 every second added onto it, which means we're now moving to the right, and second by second that just gets longer and longer and longer and longer And so because the acceleration and the velocity vector are now lined up, this is the situation where we're getting speeding up happening. And so Carrots is moving faster and faster, and now in that positive direction. So let's just play it as an animation now, just to see how that actually looks. So there you go, you can see Carrot starts by moving left, slowing down, comes to a halt at 4 seconds. Velocity vector is now moving to the right, and getting faster and faster and faster, as you can see by the velocity getting more positive, until eventually we run out of time, we start again. So just watch that through one more time. Okay, so one thing that can really be confusing when you're first trying to think about this is the fact that we can have this constant acceleration. We can have velocities in different directions. We started off negative, ended up being positive, and we just had the same constant acceleration throughout. But if you think of this interpretation in terms of these arrows, if the arrows are in the same direction, we're speeding up. If the arrows are in opposite direction, like what's happening near the start, we are slowing down or decelerating. Then that can sort of help us to get our head around what's actually happening. Right, so we've got a bit of an idea of how that works. Now let's just, before we move on, let's do an example of calculating some accelerations from velocity time graphs. So remember, when we see a graph, just look at the labels, see what kind of graph we're dealing with. Is it a velocity time graph with velocity and time? Or is it a position time graph, which is quite a different thing? This is a velocity time graph, so we can find accelerations by taking slopes rather than velocities when we had our position time graph. So question here, we were being asked to find two different accelerations, the average acceleration between 0 and 70 seconds, and the instantaneous acceleration at 25, and the tangent line's been helpfully drawn on there for us already. So between 0 and 70 seconds, let's just look at those 2 points. One of them is there, and at 70 seconds, that's that point there. So the average acceleration is really just the slope of this line here, the straight line that joins them up. And if we just were to sort of mark on some dotted lines to work out what delta V and delta T are. So delta T, well, that's just 70 seconds. The length of time interval, or the length along the bottom of that triangle, is 70. And delta V, we're going upwards. Final velocity is, let's see, that looks a bit like 250, and initial velocity looks a bit like 165, and so that is going to give me a change in velocity of 85, I think. Yes, we'll go with that, 85 meters per second. And that means our average acceleration is going to be delta V over delta T, and final minus initial, which we decided was 85 meters per second, divided by 70 seconds, which is around about 1.2142. Let's say 1.21 meters per second squared. And if we want the instantaneous acceleration at 25, let's call that A of 25. Then what we have to do for that one is we're doing rise over run for the tangent line rather than for the 2 points on the graph. So let's just rub off our previous ones. And we can see that at 25 seconds, we're basically just working out the delta V and delta T that are there in black. So delta T, well, it's just equal to 50 seconds, isn't it? From 0 to 50. And a change in velocity for that tangent line looks like 260 final velocity minus initial of 210, which is equal to 50. So my acceleration at 25 is just equal to delta V over delta T for our tangent line, which is 50 over 50, which is equal to 1 meter per second squared. So you can see that overall, my acceleration over the whole interval was around about 1.21, because there was a faster bit towards the start, which kind of influences it and makes it a bit more overall. But at that particular point in time where I took the tangent, the acceleration was 1 meter per second squared, a little bit less than the average acceleration over the interval. Okay, so now's a good time to go and look at some workshop problems and just practice calculating these accelerations and understanding what they mean. And we'll see you in the next video. Ka kite anō.